Good morning, everybody. Thank you very much for joining us today for the Hydrogen Innovation Webinar, showcasing diverse and promising applications. So this morning we have a 2-hour session, and we are joined by 7 EU-funded projects and the Clean Hydrogen Joint Undertaking, Clean Hydrogen Partnership. So first, we will hear from the Clean Hydrogen Partnership. Antonio will present for 5 minutes about funding 100+ hydrogen projects. And then from 10:10 to 11:20, each of the 7 projects will have 10 minutes to quickly introduce their project and their hydrogen innovation. And then at 11:20 to 11:50, we have a cross-cutting roundtable discussion where we highly encourage all of you in the audience to put your comments and questions into the chat, and we will address them accordingly. Otherwise, we have some prompts that we can discuss. And finally, a quick closure. I'm sorry, there's a typo there, but it will be a 5 or 10 minute closure. Yeah, so without further ado, let's get into it. I'll quickly read who is presenting what of the projects. So Ilaria will present HIPPOP, Luca will present Karma H2, Hugo will present H2 Talent, Oriol will present EVELIXIA, Carlos will present FEDECOM, and Jose Luis will present AndreaH, and last but not least, Halvor will present MECALO. So without further ado, I hand over the screen to Antonio, who will now share his screen.
Thank you so much. I'm doing it as we speak. Okay, I'm sharing, and hopefully now you have it all, correct? Not yet, because we have the same. Okay, I hope it's fine now.
Perfect, good to go, thanks.
Thank you so much, yeah, and thank you for the invitation to the Clean Hydrogen Partnership, which I'm very happy to represent today. I'm Antonio Aguilo-Rullan, and I'm a team coordinator within the Operations and Communication Unit. And I think it's already, by looking at the agenda, evident that hydrogen is not only supported by the Clean Hydrogen Partnership. I think it's very nice to see that this workshop is actually organized within the activities of one of the projects or a few projects that are not supported by us. Simultaneously, it's very good to see that some of the projects that we are supporting are actually part of this panel. So thank you for giving us the opportunity to explain very briefly who we are and what we do. So the Clean Hydrogen Partnership, it's an institutionalized European public-private partnership. We are supporting R&I in the area of hydrogen, and we have been doing this in this configuration since 2008, already within the Framework Program 7. It was the first joint undertaking. And I think what distinguishes us, if you want, from other ways of implementing European Union funding is that we are our own legal entity. So our decision-making is made up of our governing board, which is bringing on one side the European Commission, which is, of course, representing the public sector, but then we bring into that structure, into that governance, the industry, the European industry for hydrogen, and this is made by Hydrogen Europe, and then the research community through Hydrogen Europe Research. The current framework under Horizon Europe, we have a budget of 1 billion euros to implement all our activities, which is mainly grants, but we also do procurements, we also do studies. And then some years ago, on the back of the Repower EU plan of the European Commission, we were top up our budget with 200 million additional funding for implementing Hydrogen Valley type of projects, which I will mention very briefly later what they are about. It's worth to say that in our governance, we have also what we refer to as the advisory bodies. So we have the States Representative Group, which brings together representative of different ministries from research throughout the EU, but also associated countries from Horizon Europe. And we also have a stakeholder group, which is bringing the wider community on hydrogen. How are we set up? When we started the Clean Hydrogen Partnership, we developed a strategic research and innovation agenda together with our members that was approved by our governing board, and it somehow framed the way and the type of activities that we are supporting in the current framework. Our support covers the whole hydrogen value chain. We cover low technology readiness level projects all the way up to demonstration projects, so research and innovation actions across the whole value chain, as I have mentioned. We cover different green hydrogen production routes. We have a focus on green hydrogen, on hydrogen produced with renewable energy, anything to do with the distribution and the storage of that hydrogen. And then on the end uses, we cover transport and also applications for the production of heat and power. On transport, we do have a focus on what we refer to hard to decarbonize applications. So we are looking at heavy duty, road mobility, maritime, rail, aeronautic, and then on a stationary in the current framework, we have not only supported fuel cells, which is what we did actually traditionally do in the first two, if you want, versions of the joint undertaking, but we have extended our support to hydrogen turbines and burners. We have other set of activities, including activities looking at cross-cutting issues, and here we have projects looking at pre-normative research, education, awareness. One of them actually is going to be presenting today, and then also on safety. And then since the technology matured, and that, I mean, we started, of course, back in 2008 to support low TRL research for different components, for different elements. We were developing the first generation of products. We were trialing them, we were demonstrating them in the field. Of course, things were not working as expected. We were going back to research. We were developing the next generation of products. And as all these technologies can mature, we started to work with regions for some years now. And we realized that there was an appetite that was keen to implement full hydrogen ecosystems, ecosystems in which you are using hydrogen, green hydrogen to decarbonize specific sectors of the economy. And these integrated systems covering all the hydrogen value chain locally are what we refer to as hydrogen valleys. And we are also supporting those regularly in our call. And as I mentioned before, it's a key element of the REPowerEU plan of the European Commission. And we are doing that, as mentioned, every year. And then I will show a little bit what we have on that. So how do we work? We have the framework throughout this multi-financial framework, and then we have annual work programs, which of course are accompanied by annual call for proposals. So we have launched now since the 2002 4 call for proposals. The last one closed in April this year. We have received actually an unprecedented number of proposals, 212 proposals submitted to us. We will proceed with evaluations before the summertime. And then we are already working in the next call, in the preparation of the next call for 2016, which is expected to be published in January 26. The way our work programs are drafted, as I said before, our governance is made up of the European Commission and the industry and the research communities. So basically there is a co-creation in between those actors, which is then managed by the joint undertaking. We are now starting to prepare the call 26, and the process will end up towards the end of this year. And as I said, the publication of the next call will be in 2026. Should say that in terms of the rules, we are somehow bound as well by the general annexes of Horizon Europe. We have some specific conditions, but to all ends, the topics are drafted and they are structured is very much aligned with other topics in Horizon Europe, so there is no difference on that regards. So if we look back historically and if we look also at the legacy of the former joint undertaking, you may know ourselves by the fuel cells and hydrogen joint undertaking, which was how we were called in the Framework Program 7 and in Horizon 2020. You mentioned here before, plus 100 projects. Actually, we are close to 400 projects supported since 2008, with a total funding from the European Union of 1.8 billion euros. Because of the way that our EU is structured or is configured, its governance, we are established actually by a council regulation. We are asking the private members to leverage a similar amount of investments. So basically, this 1.72 billion that you see here in this slide is leveraged by an additional amount of the private members. And this is one of the particularities, the commitment of industry, the way that research and industry are working together to maximize the impacts of the projects we support. It is very important element of the joint undertaking. And again, without going to the details, you see here how the different support is distributed across the different elements of the hydrogen value chain. And you have a link in here if you want to see the details of the project. We have a website with everything available in there. Maybe one point only, and it is to say that we started back in 2008 by supporting mobility and stationary applications of fuel cells. That was somehow a little bit the main driver back in time. Then in Horizon 2020, as of 2014, of course, hydrogen was recognized also as an element that could have an important role when it becomes to absorbing renewable energy generation, power generation. The ability of hydrogen to store energy in the long term was important. Of course, the main hydrogen production route being electrolysis, the conversion of electricity into hydrogen using water as an input and electricity. Then we started to focus our support as well on electrolysis. Other routes of hydrogen production, but mainly on electrolysis. And there was a shift to somehow, we had started, as mentioned, on fuel cells development, supporting European industry, to starting to support research for electrolysis fitted to be integrated with renewables, to scaling up those electrolyzers, and that became somehow also the focus on the Horizon 2020 framework. And now we are covering to the same extent all the other elements of the value chain, especially on storage and distribution, which is something we didn't do so intensively in the past. So that's a bit for the projects. And just the very last slide, I was mentioning before that as the technology matured, back in 2014, we had one of the first integrated hydrogen ecosystems. We call them hydrogen territories in time. That's the Big HIP project. And that set the basis of what we refer now as hydrogen valleys, which are, as I mentioned, integrated hydrogen ecosystems limited to a given geography in which we are generating green hydrogen with renewables. Then this is distributed, stored as necessary, and used by different applications. So now we have 21 of these projects. We are supporting them with funding of around 250 million euros. And of course, the Horizon Europe program, if you want, we have a very limited funding. The funding that we have is limited. So these projects, on average, are funding these projects with 20% of investments. And this is why it's no surprise that the total cost are of around 1.3 million euros. So basically, these projects are really somehow a catalyzer to develop these ecosystems across Europe. And the rest is coming mainly from other sources of public funding, national, regional funding, but also from private investments. We have more details on these projects in our website, but I think what is interesting to see here without going to the details is how spread the support is being provided, covering all areas of Europe. And just to end, maybe looking at the future, I mean, of course, we are now moving into the next framework program. There is nothing yet certain. We hope that we will continue with the joint undertaking in the next multi-financial framework, but this is, of course, something cannot be set for granted. And just to add that while we are the main R&I instrument of the European Union to support hydrogen projects, hydrogen is supported also by other programs. And this is something which I mentioned at the very beginning. It's reflected in the agenda today with projects from different programs. But we are, again, very happy to participate in this type of events because probably they target a different community than what we are used to. And I think at the point in time where synergies among different programs, among different stakeholders, governance levels, it's important. We are very pleased to be able to at least let you know who we are, what we do. And if you have any questions, then feel free to get in touch with us. Okay, so that was all in brief, 5 minutes, I think. So thank you, Sia. I could not go in more details, but I hope it gave a good summary of what we do and the whole setup of the JU. Thank you so much.
Super. Thank you, Antonio. Just before you leave, on 24th and 25th June is the next Hydrogen Valley Day. I put the link here in the chat for everybody. Can you quickly talk about how is that open to the public or only to your funded projects?
Absolutely. Thank you, Sia. That's very good point. We are indeed organizing the second edition of the European Hydrogen Valley Days in Brussels, 24th of June at 2 p.m. It's open to the public. Of course, it's an in-person event. Since last year, we are trying to really go back to in-person events. It's open to the public. There is a limit of people that we can take due to the limitations of the venue, but anyone interested can go to the website, register, and then we will get back to you with a confirmation. But again, sometimes we are really sorry to say that we have to limit a bit the people that can attend because of the limitations, but by all means, please register if you are interested. It's 1.5 days where we will present all the activities that we have been doing on hydrogen valleys, but especially also on working with regions, because regions have been the main promoters of this type of projects back in time, with the support, of course, of the private sector. We will go through what we have done over the last years, but then we will showcase examples of advanced hydrogen valley projects, and we will discuss all the issues and challenges, success stories around these projects, things to do with the permitting, but also to do with the financing of these projects. And one of the main things, which is now critical, which is really about how to stimulate demand, how to stimulate hydrogen demand, especially in the mobility industry sector. We know that the projections of the cost for hydrogen are not as everyone would like. Hydrogen is still expensive. It still requires support, not only on scaling up and create volumes for the equipment infrastructure that is needed, but also in terms of R&I. We need to continue with R&I. We need to continue doing these projects more performance. But anyway, during the event, we will bring different stakeholders looking also at how we can stimulate the demand of hydrogen in this type of projects, which eventually is very needed for creating business cases and to be able to develop these ecosystems, these hydrogen valleys in a sustainable manner. So everyone is welcome. So thank you for reminding this indeed. Very good point.
Good. Thank you, Antonio. Unless there are any questions for Antonio, we will say goodbye to you for today, but feel free to get in touch with either him or I at a later time.
We will as well get in touch. Thank you, see again for the connection.
Thank you. Have a good day. Next, we will go to Ilaria from Environment Park, who will be presenting the HIPPOP project, and she will discuss raising awareness for hydrogen technologies.
Thank you very much. Yes, indeed, I represent Environment Park, which is the technical park in Turin, so Piemonte region, north of Italy, and we have been involved in hydrogen projects for more than 20 years, supporting both the local authority and the local and clusters of companies who are working on hydrogen in Italy. So HIPPOP project is indeed a clean hydrogen partnership project, part of the cross-cutting area of funding, and it is about raising public awareness and trust towards hydrogen technologies and their systemic benefit. It's a project which is about to finish, so I will illustrate the results that we have achieved so far through our different activities. But basically, our objective is to try to support the raising of the understanding of hydrogen by the public. It is important to understand that we actually covered, as a brief, we had to cover the whole of Europe, focusing specifically on the so-called EU 13 countries, so the countries which joined Europe in the latest round of accession. And indeed, we put together a consortium which also represented these countries, as you can see from here. So just a quick overview of the consortium. We are 4 hydrogen clusters, 3 research organizations, and also a strategic communication and stakeholder engagement specialist, because this indeed is one of the main focus of the project. A quick slide to tell you how we interpreted the public awareness. We thought that it wasn't just the citizens that we had to work with, but from bitter experience, which I'm sure some of you have already had as well, we thought that we needed also to try and bust some of the myths with the public institutions, so first responders, permitting, certification bodies, and decision makers. So for this reason, the project has had two kind of parallel areas of work, which will both result in some tools which we hope will be useful to raise both the awareness in the citizens, but also in the public institutions. And we have reached some interesting results so far. So how we proceeded in this project, first of all, we wanted to analyze the status quo, so the public understanding, the institutional requirements, and we gathered a number of data from the surveys, from social media, from mass media, for the public engagement aspects, and of course on the local regulations. Then we proceeded with some co-creation workshops to try and speak directly with these with the citizen and the stakeholders, and it hasn't been easy, especially for the stakeholders. And the aim of all these analyses is to end up with a set of guidelines which hopefully will guide our hydrogen projects in involving citizens and the public stakeholders and communicate to them, a communication toolkit and a web platform which will be a useful reference point to try and understand a bit more about the hydrogen technologies, and also a set of social life cycle assessment indicators which are to be used as a decision-making tool. So let's start with the social analysis. So we wanted to understand what do people think about hydrogen. So we looked, first of all, at what is the level of implementation of the hydrogen economy in the different European countries. So policies, strategies, if there were some involvement already of the citizens in this document. Then we took up some analyses which had been already conducted through public opinion surveys, and I mentioned especially one large European survey which was commissioned by the Clean Hydrogen Partnership back a couple of years ago. We reanalyzed all this data to try and go deeper into the perception of the public, and also try to understand what is the public thinking about hydrogen, also through a social media analysis. Then I'll show you a few of the first results. This is a kind of analysis that you can find in the deliverables that are all uploaded onto our website. So we found that usually people have heard of hydrogen technology, or hydrogen in general, and this is good. So there are a limited minority of people who hasn't quite heard of it. In general, people know a little bit about it. They don't have that much knowledge of it, so there is perhaps some need for trying to raise this knowledge, and maybe there is some work to be done also in terms of education, not just communication and information. As many other infrastructure, also the hydrogen technologies and hydrogen infrastructure has the same issue of not in my backyard attitude. So in principle, we like hydrogen. We think that is part of the solution for the decarbonization. But when we are actually facing an installation of an hydrogen technology next to our house, then perhaps we start to have some issues with it. But this, I think, we know is common to any kind of installation. There is a notable increase in the enthusiasm of the European citizens, but still cost of course, is considered a concern, and also the need for increasing the infrastructure. Usually Western European countries, where perhaps hydrogen has been implemented more or for a longer time, are more favorable to hydrogen as a sustainable energy source than the citizen in Eastern Europe. And also in terms of safety, there is a more positive perception of safety of hydrogen in the Western European countries than in Eastern Europe. Although, of course, we know that hydrogen safety needs to be well explained and well addressed. In general, therefore, we think that from this analysis, there is a need to raise the education of our citizens, as well as communicate clearly and communicate also with sincerity about hydrogen benefits and also hydrogen safety. For what concerns the technical analysis, we started looking at the different approaches on safety and in general permitting and certification of the hydrogen technologies. We analyzed different demonstration projects. We also analyzed the hydrogen valleys to understand how they are addressing these aspects, and we found a few differences amongst the countries. And again, this was really good to understand what are the barriers, where there are perhaps some gaps in regulations, because the regulations haven't quite caught up with what's happening, and then also the best practices from perhaps the so-called front-runner countries that are actually working already in this. So, as I mentioned initially, we had the brief to cover particularly the EU 13 countries. Of course, we covered the so-called HIPPOP countries because they are the one that we know better, and we can interact directly with our public authorities in the local language, which is an important factor as well for the interaction with these authorities. But also we looked at the so-called front-runner countries, which are those countries where we know that hydrogen technologies have been implemented the longest, and therefore there is more there is more knowledge about these technologies. Again, on the website, you can find the different analyses in the different deliverables looking at permitting, safety and certification, where you can find some representation of how the different countries are addressing the issue, and whether they are implementing those elements that we found are actually positive and supportive of the implementation of the hydrogen technologies, versus those which perhaps are a bit behind and have no regulations that we could find, or really they are not actually addressing specifically hydrogen. But here you can see, for example, for the mobility and residential sector, what are the aspects that actually made sure that the hydrogen technologies could be implemented quite smoothly. Second phase of the project, it was about the co-creation workshop. So we went out and we spoke to both the citizens and the institutional stakeholders. And the last one weren't so easy to engage. Again, country-specific difference could be found depending on the different way that the, for example, safety or permitting is carried out. But we did engage the citizens and the stakeholders in the local language, undertaking events, large international conferences, undertaking events specifically on these aspects, and we are now collecting all the different information from the different countries, and we will be using these for putting together the guidelines based also on the finding of the technical analysis. So for what concerns the public engagement strategies, so we will come out with a guideline, which is, again, to be used by those people who are implementing hydrogen installations and need to speak to the public, and also with the communication officer, perhaps the need to speak to the public. And basically what we found is that there is a need to clarify what hydrogen technologies are, using, of course, a simple language without being patronizing, being about honest and transparent about the public safety concerns, and try to also bust the myths, for example, making sure that everyone knows that hydrogen has been used for a long time, of course, so safety measures are known and can be put in place. Hydrogen is not a completely new gas to use. Making sure that the different regional contexts and also the demographic context are taken into account, because there are some difference between ages, and of course, depending on the knowledge and the implementation at the regional level, people know more or less about the hydrogen. And also we noticed again that there was a gender gap, so we need to make sure that also women are involved in this exercise. Quickly about the social life cycle assessment. So this was a tool that we decided to develop to try to introduce new indicators that could be useful for the decision making. So this is looking at how hydrogen, for example, addresses child labor, or for example, the salary or the well-being or the people that are using or implementing the technology. And our colleagues from Indea Energy in Spain undertook a specific case study to map the whole supply chain. And I think that this is quite an interesting set of indicators. Of course, it is social life cycle assessment is a tool that we are getting more and more used to, and it needs to grow also as a tool. But we contributed to that as well. And finally, the social life cycle indicators are one of the outcome of the project, but as I mentioned, these are all the guidelines that we will be publishing by the end of the project in September, and you will find it on our project, really there to be used for making sure that we grow as a continent in introducing hydrogen technologies in a safe way, and in the respect of the permitting requirements, certification requirement, and also with the with a clear communication strategy with the public. What's next? So in these last few months, we will undertake a mutual learning workshop in September to share with other project HIPPOP achievements and transferring our knowledge and tools to the different projects. So watch out for this. And also we will finalize our HIPPOP toolkit. As I mentioned, wants to collect some informative material which would support the awareness raising of both public and citizens. So again, refer back to our website, and if you have as a project some interesting video material that you would like to share, please get in touch, because we would like to keep enriching this tool. So that's it from my part. Thank you very much. These are my contacts, and later on you will see also a way to get in touch and receive more information from us. So back to you, Sia. Thank you.
Thank you, Ilaria. Next up, we have Luca from Syntef, who will present Karma H2, demonstrating waste to hydrogen technologies.
Yes, can you hear me?
Yes.
Good. And can you see my screen?
Yes. Yeah, perfect.
Great. Thank you very much, Sia, for the introduction. My name is Luca Ansalone. I'm a research scientist in SINTEF, and I'm going to talk about our project called Karma Hydrogen project, which is also funded by the Clean Hydrogen Partnership. And in particular, as you will see in this project, we are looking at developing a technology that is able to transform waste, let's say, into energy. And in particularly, we will, the Karma Hydrogen project will look at demonstrating a circular decentralized route to hydrogen production. And at the core of the project, there is a technology which is called protonic membrane reformer, and I will give you more information about it in the next slides, which will basically convert the biogas from organic waste into pressurized hydrogen. And also, it will be able to split, let's say, hydrogen from CO2, producing also a food-grade CO2 stream. And the technology will be validated in a wastewater treatment plant in Navarra, Spain, which will help, let's say, the transition, the green transition to Europe, of Spain, let's say, but also of Europe in general. A bit of information about the key figures in our consortium. So the full name of the project is called Carbon Negative Pressurized Hydrogen Production from waste using an energy efficient protonic membrane reformer. It is coordinated by AIN, which is the Association of Industry Navarra, which is a local industry association in the Navarra region. But we are in total 12 partners from 5 different countries. You can see here, let me see if I'm able to use the pointer. Yes, we have several technology providers like Corstec Membrane Science that is developing the protonic membrane reformer, but also Pentair with 2 different subsections, which are technology provider. We have end users like ERA, Shell, and SNAM. We have local communities that are those that are owning the plant and also operating, like Mancomunidad and NILSA. And finally, we have a research institute like CSIC in Spain and as SINTEF in Norway. We have a total budget of about 10 million, which go from EU, let's say, which covers for about 70% of the total budget required to perform the demonstration. As I was saying, at the core of the project, there is a technology called protonic membrane reformer, or in short, bio-PMR, which has been developed by Corstec Membrane Science. And the very interesting aspect of this technology, it is process intensification potential. Because as you see here, through this technology, we are able to combine the 6 different steps of traditional steam method reforming, which is, I would say, the most established method to convert natural gas into hydrogen and CO2 then. And we can combine them in one single step. And these 6 different steps are basically the heat that you need to provide to the natural gas stream to enter the steam methane reforming reactor. And then you have a water gas shift reaction that drives, let's say, the products towards hydrogen and CO2, but subsequently you also have to split CO2, separate hydrogen and purifying it, and then finally compress it. All these 6 steps can actually be made, can actually be performed inside the bio-PMR. The bio-PMR reactor, it is a membrane reactor where inside we have protonic ceramic membranes. And these are typically operated at relatively high temperature, between 400 and 800 degrees C. And under these conditions, they are able to break hydrogen into subatomic particles, which means protons and electrons, and then are able to drive, let's say, protons across a dense ceramic electrolyte. And in here, you can see actually the structure of these membranes. So the BZCY is the ceramic electrolyte. And then the membrane is composed of other 2 layers. You have a nickel BZCY on the top and then also on the bottom. And these 2 layers are also the electrode of the system. And at the same time, the presence of the nickel allows also for the catalytic reaction of CO2, methane, and water towards CO and hydrogen, which is then driven also with the water gas shift towards hydrogen and CO2. So basically, as you can see from this representation here, what you do is that you send methane and water inside the inlet of the membrane, and then because of the catalytic reaction of nickel, methane starts to react and you form hydrogen and CO2. But then at the same time, by circulating electricity through the membrane, you're able to extract the protons that are then recombined in molecular hydrogen on the other side of the membrane. And what you end up with is basically compressed hydrogen and CO2 plus water on the other side. And by, let's say, increasing the current density, you are able to tune the production rate of hydrogen. So you are able to tune how much hydrogen you actually pull on the other side of the membrane. And in particular, this is interesting because by doing so, you actually have the feature of traditional membrane reactor. And in particular, you are able, as you can see here, to convert methane almost entirely. We have conversion degrees up to basically 100%. And at the same time, you're also able to drive the water gas shift reaction basically towards the product, so towards CO2, suppressing almost entirely the CO yield. At the same time, this system is also quite interesting because it is a near zero energy loss system, meaning that by combining, let's say, all these 6 different steps that we talked in the beginning in one single reactor, you're able to counterbalance the extremely endothermic steam method reforming reaction, which is represented here, by basically providing heat through the exothermic reaction that are the water gas shift, the separation, which is electrically driven, and also the compression, which is also electrically driven, and therefore generating heat at the same time. Course like membrane science try to also exploit this feature and develop a reactor which is called a U-bend type gas flow. And by doing so, what they did is that they are able to basically recover, as you can see here, the heat exactly where you need it. So basically at the end or at the outlet where you will have the highest amount of heat because of the extraction and separation of hydrogen, you put it in contact with, let's say, the first part of the reactor where there is the endothermic steam method reforming reaction happening. And through this microthermal integration, you are basically able to run, let's say, this system without the need of additional heat to be provided. Here there are some, very quickly, some of the results that we have obtained just to show that we are able to achieve extremely high conversion of methane, basically mainly towards CO2, as you can see here, because we're able to compress, to remove, let's say, or to reduce the CO yield almost to zero at relatively high pressure. So we had the 30 bar in the feed. And we have also demonstrated already in the lab that it's possible to use a biogas stream. And for us, a biogas stream was a stream composed of CO2 and methane, meaning that in addition to the 6 steps that I showed you before, we can also avoid, let's say, the CO2 removal step that you need in a biogas process to enter the traditional steam method reforming reactor. We can also achieve pretty high purity on the permeate side. On the retentate side of the system, meaning that this CO2 can be already ready for liquefaction, as you will see later. And at the same time, the system, through the electrochemical compression, can also be operated so that the permeate side, it is at higher pressure compared to the feed side, which is a feature that is very peculiar for this type of electrochemical system and cannot be achieved without a traditional membrane reactor that are based on physical separation. And then finally, to conclude a little bit about the testing or the demonstration project, the demonstration test that we will have in Spain. In particular, the BioPMR technology will be demonstrated at the Arazuri wastewater treatment plant in Navarra, as I said in the beginning. The plan is to run the BioPMR unit for at least 4,000 hours, producing about 500 kilo of hydrogen per day. That will be then used for energy and mobility applications. At the same time, we will also generate about 4 tons of CO2 that will be food-grade CO2 daily that will be ready for use. So we have plan of utilizing this CO2 for CCUS application. And this is just a very simple scheme of how the system will be operated at the plant. So we will take the biogas coming from the anaerobic digester, and then we will have first biogas pretreatment. In this case, it's mainly going to be about desulfurization because there is a quite we have, let's say, to understand what type of sulfur content is allowed inside the BioPMR unit that is coming downstream. And then finally, the BioPMR will produce the pressurized hydrogen, while the CO2 stream will be sent to a liquefaction unit that will basically make liquefied CO2 that can be taken then to, as I said, utilization application afterwards. This is it from my side. Here it's just some of our channels. If you want to stay in contact with us, we have a LinkedIn account. We have a website that you can visit, thekarmahydrogen.eu, and then we have also an account on Blue Sky. Thank you very much.
Great. Thank you very much, Luca. Next up, we have Hugo. Hugo from the University of Évora, presenting the H2 Talent Project, developing hydrogen valleys in Portugal.
Hello, good morning, everyone. Thank you, Zia, for inviting us to this presentation. Our project, I hope you are seeing my screen, I guess.
Yes, if you can just go back and put it in presenter mode.
Yeah, okay,
perfect.
great.
Good to go, thanks.
So our project is an hydrogen valley. So for that reason, it's at a higher TRL, so we are not presenting research in that sense. So basically and in that way it's slightly different from what the last presentation. And basically the idea of H2 Talent is to launch a flagship hydrogen valley in Alentejo, and the idea is to consolidate the investments that are already in place in green hydrogen. And we want to develop new initiatives across the entire value chain. And this means that we are going to address production to end users. Our objective is to produce more than 500 tons per year of green hydrogen, and it will be used by several off-takers in industry, mobility, and building applications, so ET application. Furthermore, we want to explore the strategic position of Sines Port. It's a port in the south of Portugal that is meant to be valorized as a key model hub for interconnection and import and export of green hydrogen. So it is being prepared for that possibility. The project, let me just briefly mention, is composed by 7 work packages, and the fundamental work package in which most of the action will take place, it's work package 3, industrial application at the Sines backbone, and application and work package 4, applications in industry, mobility, and buildings across Alentejo. Right now, we are in the development phase, so I don't have you results to present, but I can talk a bit about our demonstrator. So basically, the valley, it's composed by 4 demonstrators. One is the most important one. It's at Sines, so it's basically it's basically an electrolyzer, small scale, but this is the first phase, a 15 megawatt. The complete phase will reach 120 megawatts, but the first phase is meant to be kind of a demonstration phase, and it will produce roughly 700. Oh, sorry, I'm having some troubles here with presentation. And it will inject the hydrogen into the hydrogen backbone, so it's being prepared a pipeline in Sines region to feed the industry there, the industry complex. And so basically we will be injecting green hydrogen into this pipeline. An alternative will be injecting this hydrogen into the grid, national natural gas grid, blending with natural gas. So the expectations, the roadmap for Portugal is that 20% of the natural gas will be substituted by green hydrogen, and we are slowly heading towards that objective. Additionally, we have 3 other demonstrators in the south of Portugal, in Algarve. It's not Alentejo region, but it's close to it. And the idea is basically use a modular system in which we have an electrolyzer coupled with a storage unit and a fuel cell, and this will act like a battery that will basically store energy in the energy community. So the idea is to adjust consumption to production. So during the day, the battery will produce hydrogen, and during the evening and night, this hydrogen will be used in a fuel cell to produce electricity. Finally, we have 2 other demonstrators in the Alentejo region, so in Évora and Alandroal. And in Alandroal, there will be a hydrogen refueling station that will be funded by our project. Let me say that it is funded by the Clean Hydrogen Partnership, so it's very good. This is a very good opportunity for our country. And we have also at this place, we will have an hydrogen bus and a garbage truck running on hydrogen that will be fed by this hydrogen refueling station. And at Évora, there will be a local blending with the natural gas from the grid, and we will be running an heating system on this blending, and heat up the municipal pool. Basically, the blend will go from 0, obviously, no hydrogen, to 20% of hydrogen. So this is basically the 4 pillars of our project. In terms of uh, the the time frame, it's a 5-year project. We are already in month 15, and we are now in the development phase of the demonstrators, and hopefully in a year time frame we will be starting demonstration. So our goal is 27 being running the demonstrator. Let me just briefly mention that our specific objectives is to promote territorial cohesion and economic growth, demonstrate integration with natural gas and electricity grids, design, construct, and operate industrial infrastructure for H2 production, and enhance social acceptance and upskill stakeholders. The overall goal, so these specific goals are below the umbrella of the overall goal, that is the development of the green hydrogen ecosystem in Alentejo, and we are covering the complete value chain. Furthermore, we should highlight that we also use digital tools and environmental impact assessments. And another very important aspect of this project is that we are promoting replication in other 2 hydrogen valleys, so in Germany and the UK. So the idea is that lessons learned from this project might be helpful to follow up valleys. We are publishing our deliverables in the Zenido community of H2 Talent, so everyone is free to go and check what we are, the information that we are producing. So basically, as we have introduced, we will be producing 500 tons per year. We are expecting to export green hydrogen from the port of Sines. This topic is a very important topic, the import and export, because there are very ambitious targets for hydrogen in Europe, and eventually we should consider in such ambitious plans the necessity to import hydrogen from other countries. In this project, we are considering the Brazil, the South America, the Latin America market, and the North of Africa market. So we also contribute to the European Union climate and energy targets by fostering renewable energy integration and sector decarbonization. Our consortium is composed by 29 partners for 7 countries, and we include universities, technology companies, and public stakeholders. We have a strong collaboration with international initiatives, as I have already mentioned, especially Brazil and Morocco. In terms of the political support, we have moved towards the political support. So a project like this, an ambitious project like this, has to have public support, and so we are basically in two aspects. We have integrated into the consortium public institutions that are related with key policies, and also are in contact with the Portuguese government in order to have support on some of the aspects that we want to implement. Please may take a note that we are sometimes a bit ahead of the legislation that is being rolled out in hydrogen, and so this political support is fundamental. In terms, now very briefly, in terms of achievements, we have already submitted many deliverables. As I said, they are published in Zenido, so if you are willing to know more about H2 Talent, you can go there. And we have approximately submitted 30% of the total plan deliverables. We have reached milestone 1, and in terms of achievements, we also managed to put together a team of 29 partners working together from 7 different countries, which is a very challenging task. Finally, our next steps is the installation and operation of the electrolyzers at the Sines backbone, launch H2 applications in mobility and buildings, expansion of Hydrogen Academy to promote skills and social acceptance. So our priority is to implement H2 Talent naturally, and also we want to submit new projects in this field to consolidate the ecosystem that is being created. So once again, thank you so much for your attention, and we unfortunately it does not appear here, but we are on the social media, so please search for H2 Talent and you will find our website, the Zenido community, our Instagram account, LinkedIn, and so on. Okay, so thank you so much for this opportunity. I will be happy to answer any questions that might arise afterwards.
Thank you, Hugo. Next up,
You're
we
welcome.
have Oriol from Blue and Rev from the EVELIXIA project, who will present hydrogen-based power and storage solutions.
Hi, everybody. Let me share the screen. Okay. There we go. There we go. So can everyone see?
Yes, perfect. Thanks.
Nice. All right. So hi everybody. I'm AndreaH. I work for Blue Energy Revolution, which is an Italian company. Let's see if I can. Yeah, an Italian cooperative, which since 2015 has been dedicated to the hydrogen life cycle. So we started out as a company that produced engineering projects, so like bespoke or custom systems, and now we've started to pivot into producing products. Our main product is our electrolyzer, which is a cabinet-based electrolyzer that is a 7 kilowatt or a 14 kilowatt version. We also produce fuel cells for the railroad market, so they're rail certified, and we're building prototypes of actual locomotives that are powered by this. So, we are very proud of this since we're a small company, and trains are rather a complex affair, but we're working towards that. And now what we're working for in the EVELIXIA project, which I'm going to talk about next, is our energy pack, which is a system that combines the electrolyzer, metal hydride storage of hydrogen, and also a fuel cell system. So it provides electrical energy storage in a single package. Just to go over the last part about the company, we also own two companies. One is called MECALO, which produces the metal hydride storage systems, and we also have the company H2Boat, which applies the hydrogen systems that we developed at Blue Energy into the marine market. And here you can see one of our ships. So, going specifically into the EVELIXIA project, it's a big project. There's a lot of partners. I think it's about 26 of them, and it's a very broad project. The main objective of it is developing a framework by which smart buildings can communicate with each other and the grid. So more specifically or technically, we're trying to build an API that allows bidirectional communication between the consumers of electricity and the producers in a standard manner, in a way that can facilitate things such as grid planning, monitoring, etc. There's also a big part of public engagement. So many of our projects or pilot sites deal directly with the population. So informing them about energy consumption behaviors, and just trying to bridge the gap between the grid and the consumer. So the project has 7 pilot sites in France, Denmark, Finland, Romania, Spain, Austria, and Greece. And all of them have slightly different approaches towards testing this platform that I was talking about. And yeah, so out of these 7 pilot sites, 2 of them deal directly with hydrogen. The others sometimes, deal with monitoring of the consumption, load shedding, alternative systems for energy storage, such as thermal storage and such. But France and Greece are the ones that deal with hydrogen. France is being led by the Entech company, which is basically a site where they're developing a system very similar to us, which I'm going to talk about now. And Greece is our site. So what we're doing in Greece is we are installing our energy pack system. So our system is basically a self-contained energy storage system which uses exclusively hydrogen as an energy vector. So this prototype for the pilot site has a 7 kilowatt kilos of metal hydride storage and 10 kilowatts of fuel cell. But we've developed this system, and I think this speaks about the capacity that these projects have to provide innovation in the private sector. using the development that we've gone ahead for with this system, we've made it so the energy pack can be scaled up into a much more powerful system. So we can go up to 30 kilowatt hours of electrolyzer, 40 kilograms of hydrogen storage, and 30 kilowatts of fuel cell within the same system. So I think, yeah, that speaks a lot about the usefulness of these funds. There's a QR code. You can see some videos that talk a bit more in detail about how the system works. It's also in the next slide, so I'm going to take a screenshot. So the system is going to be installed in the CERT Research Center in Tolomida in Macedonia. Not North Macedonia, Macedonia, the Greek province. So the building currently has 20 kilowatts of photovoltaics and a battery system. And what we're going to do there is we are going to directly connect the energy pack to the existing system. So in the scenario, for example, that the photovoltaic is higher than the load and the batteries are full, that energy would otherwise be given back to the grid. What we're going to do in this case is we're going to turn on the electrolyzer, absorb the excess energy, store it in the metal hydrides, and then when it's needed back, so when the load is higher than the photovoltaic and the batteries are empty, we're going to reconvert that hydrogen into electricity via the fuel cell. So in terms of dissemination activities for this project, we've brought the energy pack into 2 fairs, the Hanover Messe in Germany, and just last week, the Piacenza Hydrogen Expo. We found a lot of interest, and we think that because, we've been a company since 2015, and we've worked exclusively in the hydrogen market, but, we always provided things that where the user had to interact directly with hydrogen. This is the first time that we provide a product where the hydrogen is completely contained within the product and the user doesn't have to interact with the hydrogen, which is sometimes a bit, they're a bit scared to deal with it because it's not known how to deal with it, in a larger scale. So we found a lot of interest for this since the user has to deal with electricity only, which is, much more common knowledge. So we're very happy of the development that has been facilitated by this project and the interest of the public in it. So the next steps for the project are, you can see here, the delivery of the system. The system is currently on its way to Greece. It's on the truck and it's going there. And late this month, we are probably going to, late June, we are probably going to travel there to get the commissioning up and running. We are the first pilot site to be doing the commissioning, so we're very happy about that. And the system, the platform that I talked about, will start to be tested within this year, the end of this year, and next year. And the final objective is that our energy pack will be completely controlled by the system and respond to the demands of the building, but also of the grid. So thanks for listening. I hope it was interesting, and I wait for your questions later on.
Thank you, Oriol. I'm sitting here giggling because that picture of the 3 men pushing the electrolyzer is very funny.
Yeah, I wanted to show off our strong guys in the workshop.
All right. Thank you very much, Oriol. Next up, we have Carlos from Iberdrola presenting the FEDECOM project, which is the project who organized this webinar. And Carlos will talk about integrating hydrogen into federated energy systems.
Okay, thank you so much, Sia. Yes, I am trying to share my screen. I don't know if you can see the screen.
Yes, and perfect.
Perfect. Okay, okay. I believe that now it's working perfectly. Okay. Thank you so much for the invitation. And as Sia mentioned, I speak today about the FEDECOM project, integrating hydrogen into federated energy system. in this small presentation, I at the beginning I tried to describe a little bit the FEDECOM project, and after that I will be more focused in the hydrogen part regarding FEDECOM project. FEDECOM project is an European Union Horizon Europe project for 48 months of duration, and the project was funded we started in October 2022. And we are developing technical and business ecosystem to demonstrate the advantage of energy sector coupling across European community.
Sorry, Carlos, we're
Yes.
still on your title slide.
Sorry?
We're still on your title slide.
Yes. I move. I don't know why. Okay, now it's moving, or I am.
It's not.
Yes, I try to share again.
Okay.
Okay. Okay. Sorry. Okay. Okay. I try to do that again. Okay. Now?
Now we see your title slide.
Yes. Now you see the second
Yes,
one?
now it's good. Yeah.
Perfect. Now, finally. Thank you so much, Cia. Yes, as I was mentioning, FEDECOM is a 48 months European Union Horizon Europe project funded, and we started in October 2022. FEDECOM project, we are 17 partners for 7 different European countries, and the main objectives are developing a cloud-based solution for sector coupling, distributed generation and storage with high flexibility and improvement of the renewables. The second one is validating the solution in 3 pilots. That after that I will explain a little more of the 3 pilots, and at the end I will focus a little more in hydrogen pilots in order to check the diverse technical, market and climate context and so on. The next objective is developing plans for the large scale application of the solution in the following communities. The last one, evaluating impacts on OPEX, CAPEX, and all the value creation. As I mentioned before, we have 3 pilots. As you can see here, the 3 pilots. The first one is the Virtual Green Hydrogen Federation in Spain. Here we have different sites. We have 20 megawatts electrolyzer in Puerto Llano, 2.5 megawatts electrolyzer in Barcelona, and also we have some facilities in Bilbao and Uberoa. We have the second pilot is the Presidential Hydropower Federation in Switzerland, and the last one is Cross Country in Mobility Federation in Benelux and in the Netherlands. These are the 3 pilots that we have within FEDECOM project, and now I will move to the hydrogen pilot that are included in this FEDECOM platform. As I mentioned before, we have 2 sites regarding hydrogen in the first pilot, and maybe the most important one is this one is the Puerto Llano project. This is a 20 megawatt of electrolyzer that is already working, and we are supplying green hydrogen to a fertilizer industry, in this case Fertiberia, and we are using renewable energy in order to produce hydrogen, and this hydrogen is supplied to Fertiberia, and with this hydrogen they produce green ammonia, and after that some green fertilizers. This is now within the FEDECOM scope. We are trying to make different models in order to optimize the energy consumption and also the production and the cost and so on, and also with different connection with the different federation that we have within the FEDECOM project. Going a little bit deeply in this project, you can see here a little bit more details of the facility. You can see this is the electrolyzer building. We have 20 megawatt, but we have 16 stacks of 1.25 megawatt each one, but with a common burn of stack and a common burn of plant. We have, you can see also some the letter A. This is a skid timer. This is the rectifier and transformer in order to supply hydrogen to supply electricity to the stacks. We have some hydrogen vessels, some compression system, because we produce hydrogen at 30 bars, 360 kilos per hour, and we have the possibility to increase the pressure up to 60 and put in the vessel, and after that supply also during the night if it's needed. The cooling system, we are using air cooling system. At the end of the day, this is a complete facility with a lot of option to be flexible. We are connected directly with a PV facility, underground electrical line around 10 kilometers. And in this PV facility, we have also batteries, 5 megawatt of power, 20 megawatt hour of capacity. And with all of these options, we have a lot of possibilities to work with this project. Here's a picture about the electrolyzers. As I mentioned before, 16 starts of 1.25 megawatt each one. The vessels, the rectifiers, transformers. And here you can see also some details about the PV. As I mentioned before, we have a direct connection with the PV. The facility is 100 megawatt. We are taking part of it. So the electricity is going to the grid. And also we have the batteries, as I mentioned to you before. This is the first pilot that is included in the FEDECOM project. And we have the second one, that is a hydrogen refueling station. This hydrogen refueling station is located in Barcelona, and we are supplying hydrogen to Barcelona buses for the TMB, Transportes Metropolitanos de Barcelona. The TMB bought some buses, and now they are increasing the numbers. After that, they published an open tender, and we apply, and we won, and we built this filling station. We have now 2.5 megawatt electrolyzers. We are producing hydrogen at 30 bar. We have some hydrogen storage system at 30, 305 and 450 bars, different level pressure, and we have some compression system, and also some chillers and some dispersers in order to put the hydrogen into the buses. And now we are filling close to 60 buses, and for the moment we don't need to increase the capability of the electrolyzer, but maybe in the next if the number of buses continue growing, maybe we will need to scale up the facility. And here you can see also some picture about the facility. As you can see, we have a lot of empty spaces in order to make the expansion. Now we are making expansion for some vessels, some compression system, and some dispensers. Yes, and as this filling station that is also involved in this FEDECOM project, and we are doing similar works like in Portugal project. We are using optimization tools in order to optimize the energy consumption, and also to optimize the price of the energy. And this is maybe the most interesting thing that we are doing in this project regarding hydrogen, and also the connection for these hydrogen pilots with another pilots that are involved within FEDECOM project. And I believe that this is all that I have to say today. And yes, I don't know if you have some question. I am more than open to answer the different questions that can appear.
Thank you very much, Carlos. Next up, we have Jose Luis from the AndreaH project presenting research on ammonia cracking for hydrogen applications.
Thank you. I will start sharing. You see my presentation?
Yes, good, thank you.
Okay, thank you. Thank you, Sia, for inviting us to participate in this webinar. Sorry, I'm going to talk about a project that was approved in the frame of a topic in the Clean Hydrogen Partnership, was on liquid hydrogen carriers, more specifically on ammonia. So the title is ammonia-based membrane reactor for green hydrogen production. And we know that the ammonia hydrogen can be produced in many places, and ammonia is one of the energy carriers we have for hydrogen. But the point is to how we can recover the hydrogen from ammonia when transporting from the production side to the end user side. So the idea of the project is to use a membrane reactor, the concept of membrane reactor, and to improve the conversion of the cis-blend. Is when you have an equilibrium reaction, is you remove a product at the same moment you produce, you are shifting the reaction to the production side, so you increase the production. And here is the concept of membrane reactor. You have integrated the reaction and the separation through a membrane in one step, and then you are able to work at lower temperatures, having 100% conversion at lower temperatures. In this case, the process is addressing the cracking of ammonia by using a catalytic membrane reactor, and also developing new catalysts, and also having periodic open cellular structures for improving the heat and mass transfer in the reaction zone. So basically, the idea is to develop and demonstrate a 10 kilograms hydrogen per day scale prototype. Developing also new catalysts with low or without. We have worked in both lines of ruthenium content, and also developing this catalyst over the 3D printed periodic open cellular structures, and also to include novel membranes that are carbon molecular cell membranes for selective separation of hydrogen during the production process. And we have a final state that is some polishing of the hydrogen, removing the traces of ammonia, because if you want to use for proton exchange membranes, hydrogen should have only ammonia lower than 0.1 ppm. So another application, a study scenario application, could be higher, but for fuel cells and PEMs, that should decrease 0.1 ppm. So besides this, we will also do life cycle analysis and cost analysis and health safety analysis in the project. And we elaborate some business cases on this prototype, and also the promotion of the AndreaH results and his impact. We are 9 partners for 4 countries, and we are 66% of the partnership is from the small scale industry, and we cover all the value chain from people, companies specialized in materials development like Umicore, for instance, or energy multinational companies like Iberdrola, and also energy storage provider, that's VTTI, that is, they have bunkers and in the Rotterdam ports, for instance. They have, we will test the prototype there, by the way. And also we have research organization, universities like Eindhoven Technology University, as Centro Nacional de Ricerca in Italy, and Tecnalia, where I'm coming from. And RINA is the entity working in life cycle analysis and all life cycle cost and health and safety analysis. So basically, we have 3 main steps in the project. In the first part, we are working in developing the building blocks, we can call like this, that are the membranes and the catalysts and the periodic open cell structures and solvents for the final polishing step, where we have the Umicore and CNR are involved in the catalyst development. Catalysts supported on POCs and open POCs or foams. And Tecnalia developed more in developing carbon membranes with Eindhoven, and solvents also is Eindhoven involved in the solvents. Then we have the membrane reactor construction, that is mainly Eindhoven involved on this. And the testing and Tecnalia will develop the membranes, and Umicore and POCs with the we have the POCs for the prototype. And the testing will be carried out by VTTI with the support of Eindhoven in the Rotterdam port. They have a facility where they have bunkers there. Then we have all the transversal activities regarding life cycle analysis and dissemination and communication and modeling as well. Basically, we will have 4 main exposition results that will cover from the reactor to the catalyst. We have 2 families of catalysts that are being studied, by the way. And then we have the carbon membranes, they are the first time that are developed, trying to use carbon membranes for selectively separation of hydrogen from ammonia and nitrogen, and also the novel solvents for polishing of hydrogen in the permeate side of the membranes. But overall, the key exploitable results is the advanced ammonia cracking system. And with this, we want to contribute to different transversal targets. That is to keep in Europe the technology leaderships, developing innovative reactors and catalysts for cracking of ammonia, and also reduce the use of critical raw materials in ammonia cracking, and also improving. We're going to study and improve the economics of the ammonia the hydrogenization process, and developing business models for considering the transport of ammonia from corridors outside Europe, for instance, to Europe, and later on having a centralized or decentralized cracking system. And so the idea is to contribute to have secure the energy supply to Europe instead of using fossil fuels, using ammonia as a hydrogen carrier, energy carrier, we will say more, and also in trying to support the decarbonization of the society, because there are sectors where it's difficult to abate the CO2 emission, and the idea is to facilitate the hydrogen introduction in this sector, and ammonia can contribute to this. And we talk about the joint undertaking. There was some targets in the frame of the call that to develop a range of hydrogen carriers that can be used commercially for transporting and store the hydrogen. It's more easy to transport hydrogen and in ammonia. We know how to transport ammonia since maybe more than 70 years, because it's used in the fertilizer industry. So the cryogenic hydrogen transport and storage is more expensive than the ammonia storage. Ammonia is already liquefied around 1 atmosphere, around -36 around degrees. So it's than the cryogenic temperature you need for the hydrogen, or if you are at 8 bars, you are at 1 atmosphere, you can have it at room temperature. So we are going to study also and simulate the techno-economic analysis of well to tank for when we delivery hydrogen as in ammonia for 3,000 kilometers ship transfer. That is like going from Morocco to Rotterdam. That already I've seen initiatives to have this. And then finally, we also going to study to reduce the energy consumption for production of hydrogen and transport then to the end user. So we will focus on these activities. We have to think that here we can have the conversion around 425. You have already 100% ammonia conversion, and you have also high recovery of hydrogen. So that means that you work at lower temperatures and the standard between brackets standard cracking system. And so that is an overview of the AndreaH project. If you would like to have more information, you can access this link in the public website, and you will have also the LinkedIn link there, so you can have you can also register to receive newsletters or in the LinkedIn of the project LinkedIn as well. Thank you for your attention.
Thank you, Jose Luis. Last but certainly not least, before roundtable discussion, we have Halvor from Sintef presenting MECALO, the exploring new hydrogen innovations.
Hello. Trying to set this up. So this worked this morning. Is it still working?
Yes.
Okay. Thank you, Zia. Yeah, thanks for the introduction. I'm going to talk about the MECALO project. So the full name of our project is CO₂-free production of critical raw materials using hydrogen. And you might wonder how we get to the acronym MECALO from that. And it's hidden within the background of the project. So our application is within the field of metallurgy, and metal production is a large contributor to CO₂ emissions globally. And that would be the case even if we had a fully decarbonized grid and had the pure energy, because carbon is a key part of the chemical reactions that produce the metals. So even with the pure energy, you would have CO₂ emissions with today's processes. And I'm sure most of the audience today know that you can replace hydrogen for carbon, for example, in the production of steel. So there's a lot of interest in making CO₂-free iron, where you replace carbon with hydrogen, and then your byproduct becomes H2O, which is water. And that's, of course, vast improvement. Unfortunately, hydrogen is less reactive than carbon, so it does not react with all metal ores. For example, the critical raw materials manganese and silicon, you cannot make them with hydrogen just like you can with iron. So in the MECALO concept, we want to actually keep using carbon for the metal producing reactions. So we will have carbon reacting with our metal ore, creating the metals and the CO₂, but then instead of releasing the CO₂, we will react it with hydrogen in a methanation process over a catalyst. This will give us H2O as a byproduct, and we will produce methane. The methane we can then decompose in a pyrolytic process into solid carbon. We will also get hydrogen, which we can take back into the methanation step, and then the carbon that we can produce can be synthesized into a raw material that is fit for metal production. So if you look at this, you have the carbon is kept within the loop of the system. It never leaves. So that's why we have the name metal production with carbon looping, or MECALO. And if you zoom out and look at what's coming in and out of this loop, we have metal ore going in, and we have hydrogen going in, and we have water and our metals coming out. So if you zoom out, we have managed to indirectly, at least, replace carbon with hydrogen, even in the production of these more challenging metals. But of course, it's not as easy as all this. The main ambition of MECALO is to demonstrate its innovative concept of renewable hydrogen and carbon looping for CO₂ neutral production of silicon and manganese. And to do that, we have to overcome a few challenges that we are working on. The project has been going for about 6 months now, so I will mainly be talking about what we will do. The first challenge is to optimize the gas conversion, that is the conversion of the CO₂ into solid carbon. And that means that we have to optimize together the methanation and the plasmolysis steps, because neither of these two reactions will be completely complete. So from the methanation step, there will still be CO₂ and hydrogen in the gas stream going into the plasma reactor. The methane is decomposed in the plasma reactor, which is why we call it plasmolysis. And likewise, not all the methane will decompose. So the complete optimization of these two in order to convert CO₂ into solid carbon will be very important. And then when we have our carbon, unfortunately, the carbon coming out is a very, very fine powder, and it's completely unfit for metal production. If you put a powder into a smelter, it will just blow out with the off gas. It will never do anything. So we have to make agglomerates, and in order to get the carbon to stick together, we need some binders. We will use biogenic binders, so it will remain CO2 neutral, and we might also put some of the ore into these agglomerates. And it may be surprising to those who are not working in the field of metallurgy that carbon is not carbon. So the properties of these agglomerates will be very important. In the production of manganese, you want to have a carbon that is not reacting at all until it's in the core of the furnace, and then things starts happening. So you want a very unreactive carbon. For silicon, on the other hand, there will be gaseous species that carry silicon with it, and you need those species to react with your carbon so that you capture the silicon. If that doesn't happen, you will have silicon loss and unacceptable yields. So we need to tune our carbon material to the different metal producing reactions that we will be carrying out. So once we have our raw material, we will use it to make metal. In the end, we will do this at TRL level 6 and make hundreds of kilograms of metal. Before we get so far, we will also do a lot of bench scale and laboratory scale trials to see how our raw material works in metal producing, and then of course give feedback to the raw material synthesis people, so to update their recipe. Another challenge is that if you just do these things step by step, it will be very, very hard to get good numbers for hydrogen efficiency and energy efficiency. So we need to optimize the whole process, and in order to do that, we also are creating digital models of the whole process. And finally, we need to evaluate the sustainability of our concept, both in terms of economics, so technical economic assessment will be performed, also environmental assessment and life cycle assessment, and we will also look into how to best integrate the MECALO concept into different hydrogen value chains. These are our partners. The project is coordinated by SINTEF in Trondheim. The methanation part of the gas conversion step is done catalytically by Johnson Matthey, and then also together with the catalysis group at SINTEF, and then the pyrolysis of methane is done by Sakovin in France. They have a plasma process for this. The raw material synthesis, we use biobinders that are developed by BTG in the Netherlands. The agglomerates themselves are made by ITPE in Poland and GLAT in Germany in close collaboration with the metal producers Elkem and Eramet. These are the big industrial partners that actually make metal today, and also together with SINTEF. Most of the modeling and simulations are done by PDC, Process Design Center in the Netherlands, supported by SINTEF, and the metal production is handled by the industrial metal producers Elkem and Eramet, together with SINTEF. The techno-economic assessment, PDC will be doing that based on their process models. SINTEF will look at hydrogen integration, and then we have the Luxembourg Institute of Science and Technology, who will do the LCA and environmental assessment. And then always when you're working with hydrogen, you have to look into safety. In addition, we have all of these powders that are new materials and that can have all kinds of different safety issues. So we have a task on safety, which is carried out by Ineris from France. And then finally, our dissemination and communication partner is ETA Florence from Italy. If we succeed, then we will actually have CO2 neutral production of silicon and manganese, which are two critical raw materials that are very, very important for the new green technologies that are coming. So these are materials that the EU will need, and if you look towards the future, by 2050, the MECALO concept could allow Europe to make, in a carbon neutral way, 86% of the silicon it needs and 50% of the manganese it needs. So we will require less import of these materials. We would also require less imports of coal. 9 million tons could be replaced by hydrogen that we can make locally. And it would, of course, save 33 million tons of CO2. So this is in total. Hopefully, it will be a strong contribution to the European Union's independence and climate neutrality. That was what I had. So thank you for the invitation and thank you for your attention.
Thank you, Halvor. Next up, we have a portion where I will ask all of the speakers to please put your camera on, and when you speak, unmute yourself. So we've heard from 6 technical hydrogen projects and 1 more awareness-raising project. There's a bit of a push and pull, and I've heard several times about the policy legislation lagging behind the innovation. So how do you deal with the push and pull in terms of making sure your innovation stays aligned with policy or market trends, but also, on the other hand, what recommendations can you provide to these policymakers in order to stay up to date with the innovations that you're developing? Anyone? It's too difficult. Okay.
So no, so I thought I might wait because my project is a lot of the other people are more on the hydrogen industry. I'm more on the hydrogen use industry. But for us, one of the most important, I believe, policy changes or most important policies will be the carbon border tax. Because if we can implement all of this in Europe, but it will be more expensive than carrying on as we do today. No matter how cheap almost you make the hydrogen, it will be more expensive. So for us, having some kind of mechanism that prevents carbon leak through imports will be, I think, the most critical that I see. And then, of course, we need to buy the hydrogen. And maybe someone else can comment on how we can get to the point where we can get that hydrogen most affordably.
Oh, I believe that from a point of view, yes, as you know, we have several projects regarding hydrogen, and I believe that the key challenge in order that the project go ahead is that the regulation will be in place in a clear way. No, you know that now RED III is under transposition in different countries, and this is not in place yet, at least in Spain or in a lot of countries. And I believe that we need this regulation in place in order to be sure that this project will go ahead. I believe that from a technical point of view, it's true that always you can optimize the electrolyzer and everything, but now we have technology in order to can produce green hydrogen. But the thing that we need is maybe that this transposition will be transposed very soon, and to create stability in the market and in order that the project go ahead.
If I may, I think one of the points that came out from the analysis that we did is also issues about procedures. And I guess that there are differences, and we saw that in some countries it works better if there is more communication between those who are implementing technologies and those who need to authorize or license the technology. So if they start since the beginning this communication, then there is the opportunity to understand better what are the risks, and therefore help also the authorities to try and get the permitting more smoothly. Of course, this is aside from regulations being in place, but then really is a question of then speaking to the people who in the region or in the municipality need to provide these permits. And actually one regional authority in Italy was quite transparent in saying that from one side they have perhaps a strategic drive towards hydrogen implementation, and on the other side, the colleagues from the authorization and permitting do not quite need to, of course, to abide to the regulation in place, and therefore maybe they are they need to be a bit more careful and to slow down these things. So of course there needs to be more integration between these functions and together try to push the regulatory aspects, whether they are at regional levels or perhaps at national levels.
Yeah, on a similar note, we also work in Italy, and what we found, especially since we work in rather small plants, so we work under 100 kilowatts, and permitting and safety obviously is a bigger overhead. It's kind of a fixed cost for us, and what we find is that even though the regulations are more or less harmonized on the industrial level, when we want to commission a plant, we have to speak with local actors, which have vastly different views as to how to make this go ahead, right? So here in Italy, you have to talk to the firefighters of this province, which might have a completely different opinion than the firefighters on the next province. And even though the system is the same and it's perfectly agreeing with the regulations on an industrial level, there's, as Ilaria said, this divide between the project and the going ahead with it, which I feel like requires some sort of standardization and uniformization, like other dangerous things have. You know, you can install a boiler, a gas boiler at your home inside your house, and there's a procedure for that. Obviously, I'm not saying that hydrogen should get to that level yet, but certainly the procedures for permitting and the such have to be improved.
Okay, thank you. The next question I will raise is about integration and interoperability. So for integration, how can hydrogen systems be better integrated into existing energy and mobility infrastructures? And for interoperability, what role do digital platforms and system interoperability play in accelerating hydrogen deployment? For example, I know, Oriol, you mentioned EVELIXIA is developing an API. And so I'm assuming there's standardization issues and hardware interoperability, things like this that you're dealing with. Yeah. I know in FEDECOM, we're also developing a platform. I've seen digital twins be mentioned today. How do these digital platforms, you know, accelerate the use of hydrogen in your projects?
Yeah, absolutely. With regards to interoperability, that's one of our biggest hurdles, because we have a lot of experience with hydrogen. And as I said before, we install it in smaller plants. So we cannot make custom power electronics, for example, because we are working with 20, 30 kilowatt systems. So we want to use commercial systems, but commercial systems are not prepared to accept this. So if I have a fuel cell that is charging a battery, which is controlled by an inverter, and I charge the battery in parallel from the inverter gets confused because the battery is charging itself, which doesn't make any sense. So I have to talk to the inverter in some way, and maybe it's not prepared to accept that kind of logic. So what we're trying to do is working with our suppliers in order to add these specific functionalities in order to make hydrogen on a smaller scale feasible. With regards to the EVELIXIA project, yeah, this is also one of the biggest obstacles, because we're dealing with many systems, many types of energy systems. So generation, storage, of many different types of heat. We're doing gas, electricity mainly. So one of the biggest problems is coordinating everybody and establishing a common language by which we can all speak to each other.
Okay, if there's nothing else on digital platforms, Ilaria, you presented the familiarity survey. So in terms of public trust, and also someone mentioned that I think it was you, Oriel, again, who mentioned that hydrogen it's scary a bit and it's unfamiliar. People don't know how or even want to interact with it. So how can we improve public trust or acceptance from the public in terms of hydrogen being a common way to get electricity?
Well, this is quite interesting. We did through the public workshops. There were, of course, a set of questions that were raised, which were common throughout the countries, and those were exactly about safety, for example. And then there were questions which were more related to the local different situation about, the different countries or even the different single municipalities where these people came from. So I think that from this in particular, what we learn is that you need to be transparent, you need to be honest. So we do not want to say that hydrogen is a perfectly safe gas in itself. I mean, hydrogen is an explosive. Hydrogen has some peculiarity that needs to be dealt with. And of course, this cannot be unsaid. At the same time, we need to make sure that people understand that even methane is an explosive gas and it has its own dangers. So it's just what we need to make sure is that everyone understand that we know how to deal with the explosiveness of hydrogen. So it's not that it's a completely unknown gas. And I think we felt that there is this perception amongst the public that hydrogen is a completely new molecule that nobody knows how to deal with. So it is really important, in my opinion, to be transparent and honest, but also to reassure that there are the means for addressing certain issues. For example, safety, which is the one that comes up more often. And I think is also making sure that you can demonstrate that there are hydrogen installations throughout the same country or other countries, and these installations works perfectly, and have been working perfectly for many years. I think that's an important message also to be given. And I'm not talking in this case only about installation in industry, but also installation in the public domain. So, for example, the fact that there are hydrogen buses which run around different cities without major problems, that needs to be communicated. So we had a case, for example, of a local authority wanting to introduce hydrogen buses and having people living around where they are planning to put the refueling station, complaining about the risk of explosion. So, of course, they need to talk to these people, they need to understand their concerns and show that what are the measures that they are putting into place, and also, in my opinion, also showing examples of successful implementations of these same aspects.
Okay, if there's nothing else on that. So having been involved in EU projects for 10 years, I know that pilot replication is a very important aspect. All of us except HIPPOP have presented today pilots. So in terms of replication and scaling up, what do you see as the main barriers? We've even heard today non-EU countries being, targeted during the project as potential adopters. What are the main barriers, either within or outside of Europe, towards scaling up and replicating these pilots?
Yes, I can say that I believe that the main barriers are again the legislation in place, the regulation in place, and also the incentives, no? Because you need that the companies need some incentives in order to install green hydrogen. You need obligation and you need incentive also, no? And I believe this is the key, no? Because you can build a pilot in order to see that it's working nice, but in order to scale up, you need to build 100, 200 megawatt of electrolysis facility. And if the regulation is not in place, it will be impossible that some refinery, fertilizer or chemical industry will accept to buy green hydrogen at the real price that the green hydrogen have. No? And I believe that the regulation is key in everything.
Maybe I can add something else here. It depends on the level, of course. I fully agree with Carlos in the remarks. But when you are talking about prototypes at low TRL, it's also very important when you set up the project to include partners or companies, we will say, that are able to produce a large scale. Because you want to duplicate or you want to increase the size, you have to have all the value chain of the partners providing the catalysts, the membranes, or whatever you need, should be able to produce this as also a larger scale. Because in some projects you have you do tests with a smaller scale, and then who is going to later on take over and this increase the manufacturing readiness level of this material you need. Because one thing is the prototype, you have a scale, but if you multiply by 100 or the production or the replication in many places, you need someone who is able to provide all the materials you need to have this replication, by the way. So besides the cost, and also a cost is you don't have incentives, it's difficult to have people because of as you compare the green hydrogen or gray hydrogen costs is very different. As you go to the United States, as you have carbon capture, they can produce hydrogen with reforming, but with carbon capture. So here in Europe, you have a different policy. You are focusing more in not having going to green directly. And this has a cost, and you have the CO taxes, but then it's at the beginning, because it's a learning process, also you will decrease the cost. It might be in 10 or 15 years, because you learn also how to deal with large scale of photovoltaic connected a large amount power of megawatts of fuel cells. So it's also a learning process, not only in the mass production, but also in using the system. and this has a cost for starting and have a bigger scale and learning from there. As Carlos says, the cost. But besides, you have to have all the new things you develop. You should have companies able to provide the materials and components at large scale as well.
Yeah, thank you. So I think that perfectly transitions into the last question. So this one is personally my favorite. Carlos mentioned that we need incentives, and Jose Luis mentioned about cost. I've heard today economic assessments were being developed. What is the main compelling economic advantage? We know the environmental advantages, but for the economic advantage of your innovation, how does it help the adoption of hydrogen? How does it maybe lower the cost and increase the adaptability of the solution within your project?
So maybe I can answer. For our sake, like I said before, we're not competing with the metal production as is. For us, the competitor is metal production with the carbon capture and storage, and we will be cheaper than that, and we will not need the storage, which will, I mean, in Norway, we have the possibility of storage offshore, but not everywhere will you have storage available. So that will be if it's easier to make hydrogen than to find a place to store the CO2, then that will be an advantage for us.
Okay. Unless there's anything else, I will thank everybody very much for the speakers, both the attendees and speakers alike. And as I say goodbye, I will put up this slide on the screen for you and leave it there. These are the newsletter links of each of the projects. Feel free to take a screenshot and rewrite the URL. As well, we will, for all of the projects who want to make their slides public, we will publish them across the different project websites. And with that, I will leave you exactly at 12 o'clock to enjoy the rest of your afternoon. And again, I thank you very much. I found it very interesting, and I hope you all did too. Have a wonderful day.
Thank you so
Thank
much.
you so much.
Thank
So much for the organization,
Thank you
Zia.
for-
Yes,
Bye, everyone.
Bye.
Bye.
Thank
Thank you.
you. Bye-bye.
Bye.